Most people have seen histograms in their high school classes, so we're not going to spend a lot of time on it in this class, but we will do a quick review. Histograms are a way of graphing a single continuous numeric variable. The continuous numeric variable being graphed in these two examples is energy consumption. The units of the variable, which is in this case BTU, goes on the x-axis. And either frequency or percentage is graphed on the y-axis. The x-axis is broken into intervals that span the range of the data. So in this example, they're broken into intervals of 100. So we have an interval from 100 to 200, 200 to 300, 300 to 400, and etc. Then the height of the bar indicates the number of observations that fall in that interval. These are graphs of the energy consumption by state. So state is the observation, and there are 50 observations. And a quick note here before we go on, frequency is just a fancy word for count. So those two things mean the same. And so if you look at this graph, you can see that there are two states between 100 and 200, 19 states between 200 and 300, 16 in this interval, 9 in this interval, 1, 2, and 1. And if you add those numbers up, you'll see that they add up to 50. And a quick note on a little math notation, the square brackets mean includes, and the rounded bracket means does not include. So this is everything starting at 100 up to but not including 200. So for example, if there was an observation that came out right exactly on the line, like if it was exactly 200, it would be included in that 19. So just a quick math note on percentages. 0.04 equals 4 out of 100, which equals 4%. So 0.04 and 4% are the same. And you probably remember being told that if you have a number and you want to convert it to a percent, you take the decimal and you move it over 2 spots. So it's usually easiest for us to think and talk about numbers in terms of percentages, but anytime we do any calculations, like if you're going to put it in your calculator, you need to put in 0.04. So back to our graphs here. The second graph has percentage, which is expressed in the decimal form on the y-axis. And on this graph, the heights of the bars, so this one goes up to 0.04, so there's 4% in this interval. This bar goes up to 0.38, so there's 38% in that interval. And that's coming from 19 total observations, like we saw on the first graph, divided by 50 total observations in the data set. And if you do that, punch that on your calculator, you'll get 0.38, which equals 38%. So now let's take a step back and look at the overall shape of these two graphs. The shape looks the same. And that's because it is the same. The shape is identically the same. So note the shape is the same regardless of whether frequency or count or percentage is graphed on the y-axis. So what's the point of having two graphs if they look the same? And in honesty, if you have only one group of data that you're looking at, it doesn't matter which one you look at. It's just a matter of personal preference, really. But what if you're looking at more than one group and you want to compare the graphs, which is the situation we have in the example on the next page. And in this example, we're using some data from the 2015 Red Sox. And this data set actually has lots of variables. And two of the variables are handedness, whether they bat left or right, and the number of games they have played. So player is an identifier, and each row or observation in the data set is one player. Handedness is a categorical variable, and so I've split this into two groups, the right-handed and the left-handed, and for the purists out there, I did actually include the ambidextrous ones in with the left-handed. And games played is a numeric variable. So games played is our numeric variable that's on the x-axis. So in this first graph, we have the number of games played by the left-handed players, and here we have the number of games played by the right-handed players. So we can see here that there are a lot more games played by the right-handed player. So why is that? Are the right-handed players better? Is that why they play more games? No, it's because there are more right-handed players. So in the bottom two graphs, we have percentage on the y-axis. And so now we can compare the two groups, and we can do a fair comparison. So for example, we can look at this interval from 0 to 25, and we see that a little more than 4% of the left-handed players play between 0 and 25 games. For the right-handed players, it's a little less than 4% from 0 to 25. Looks pretty similar in the next two groups, and we see that a difference though is coming out. There are more right-handed players that play like 125 to 150 games. So it does look like the right-handed players are more likely to be the players that play a lot of games. But it's only a pretty slight difference, actually. The general shape is pretty much the same. So the important point here is that it's important to use percentages on the y-axis if you're going to compare two groups. Otherwise, it won't be a fair comparison. You can't make direct comparisons between two groups if you're using the counts, because one group could be a much larger or much smaller group than the other one. So at this point, you should turn to page 4 in the Orange book. And for those who don't have your books yet, I'll include a copy of this page in Brightspace. Probably the most important thing we can do with histograms is to look at the shape of the distribution. So on this page, we have 6 distributions and 6 histograms. The histograms have no labels or numbers on the axes. So you have to just think about, if you made a graph of these things, what would the graph look like? Think about how these numbers might be distributed, and then try to do a matching with the 6 graphs on the bottom. So work by process of elimination. Which one of these do you think is the easiest? And then kind of work that way. So this is not an easy thing to do, but work on this and do your best. So at this point, you should pause the video and give this a try. So which one of these might be the age of the female U.S. population. So could it be this first one? This would say there's almost no babies. So that can't be right. This would say, oh, there's a lot of babies and kids and then hardly any adults. So that couldn't be right. Let's jump down here to this one on the bottom. We have a lot of babies, young people, and then kind of level across here. And then, it tails off. There's only like a few people that make it to 100 years old. And this little bump right here is the baby boomers. So this is A, age of U.S. population of females. The next one is age at lung cancer diagnosis. So which graph is that? Well, this one right here says only a few people get diagnosed when they're young. Then as you get into the older age groups, this is where you see the peak of the diagnoses, and then it tails off because, not very many people get diagnosed when they're 100 because not very many people live that long. So this one is B. So I said work by process of elimination, and I'm going to skip this next one, C, miles of coastline, because that's a little bit of a tough one. And let's go to commuting distance. Let's skip that one also. How about E, number of siblings for UMF students? Of the remaining graphs, which one would that be? Well, this graph right here says, well, there's a lot of people with, 0 or 1 siblings, maybe less with 2, less with 3, 4. And so we get a lot of numbers here, and then it tails off. And so that one is E. What about F, the height of all UMF students? Okay, well, this graph here says, well, there's a few short people, and the bulk of the heights are in this group. We see kind of 2 peaks, and one peak is for females because we have about 70% females, and then we have 30% males, so you see a peak around their average height, and then it tails off. So this one is F. And that leaves us with these 2 graphs, which are quite similar, and miles of coastline for 48 states, and the commuting distance for UMF students. Both of these graphs have a big bulk of the observations right down here at 0. And what do these 2 distributions have in common? Okay, well, there's a whole bunch of states that don't have any coastline because they're in the middle. So their coastline is 0. Okay, our commuting distance, okay, we also have about half of our students that live on campus, and of the ones who don't live on campus, a lot of them live within a mile. So there's also a big peak, a big group that has 0 or 1. But some people commute from quite a distance. So these 2 are kind of hard to tell between those 2 because they both have that same feature of a lot of observations at the 0 to 1. As it turns out, this one right here is C, miles of coastline for the 48 states. This one right here is Florida, and this is where my daughter just moved. This one is California, and there's a reason that I made the graph only of the 48 states, because Alaska, if we put Alaska on here, it would be like so far out here at 6,000 that everything else would have just been all pushed together with one little state sticking way out there. So these are outliers, which is a word that we'll talk about more in the next section. So those are unusual points. And that leaves us by process of elimination that this one is D, and this right here is about 30 at 30, where we see this little hump, and that is like the distance of like Augusta and Skowhegan. And that brings us to the end of this video. And next you should watch the video about means and medians.